Last time we discussed the regular pumping property, which is a property that is true about all regular languages. We can write down the regular pumping property in the following way, that RPPA is that there exists some number p, and we know this number is really the number of states in the machine, where for all s inside of A, such that the length of s is greater than or equal to p, there exists x, y, and z, which are strings, where s is equal to x, y, z, and the length of x, y is less than p, and the length of y is greater than 0, where for all I inside of n, x, y, I, z is inside of A. Now this property is true about all regular languages. In other words, for all A inside of reg, PA is true. This is the regular pumping property, and this is what's called the pumping lemma. Now the thing is that we don't really care about this property itself. What we really care about is we would like to prove that there exists something that is inside of all, but not inside of reg. Okay? So we would like to prove that this is the case, that things like 0, 1 are inside of fin, things like 0 star, 1 star are inside of reg, and that things like 0 to the n, 1 to the n are inside of all. Now, let's think for a moment about how you might try to construct. Actually, let's hold that off. Sorry. So what we really want to do is prove that 0 to the n, 1 to the n does not have the regular pumping property. In other words, what we want to do is we want to prove the negation of RPP on 0 to the n, 1 to the n. That's what our goal is. So what is the negation of this? So the negation of it is clearly just this negated. But actually there's something that's kind of nice, is that when you negate an exists, it becomes a for all, and when you negate a for all, it becomes an exists. So that means that what we really want to do is prove the negation of RPP, and it is the following. It says that for all p inside of n, there exists an s inside of A such that the length of s is greater than p, greater than or equal to p, where for all x, y, z inside of sigma star, s equals x, y, z, and the length of x, y is greater than p, and the length of y is greater than 0, there exists an I inside of n where x, y to the I, z is not inside of A. That is the property that we would like to prove about the language 0 to the n, 1 to the n. Now, when you do a proof, you can kind of think of for alls and exists as being like a game, where whenever there's a for all, that means that your opponent gets to choose the value. So if we were trying to prove not RPP about 0 to the n, 1 to the n, that means that our opponent gets to pick a p that is somehow the most dastardly weird p possible. And then whenever there's an exists, that's something that you, the person doing the proof, have to come up with the actual witness for the value. So we would have to come up with a string s that is definitely inside of A, whose length is greater than or equal to p. Then there's a for all, which means that our opponent then chooses x, y, and z, and exists, that means we pick I, and so on. So let's try to do this proof. Now, to get ourselves familiar with how we can do this proof, let's imagine how we could try to solve the 0 to the n, 1 to the n problem ourselves, if we were to do it, with like a programming language or with a DFA or something like that. So let's start with trying to do this inside of C. So we want to write 0 to the n, 1 to the n in C. Here's how you might try to do it. You might write something like this. We might say int count equals 0. And then what we would do is we'd say something like this. We'd say something like while 1, like basically an infinite loop. We would say if get C, that's something that gets the next character, is equal to 0, then what we'll do is we'll do count plus plus. Otherwise, we'll break. Okay? And then we'll have a while. And we'll say, well, what's the right way to do this? While the count, actually, yeah, here's what we'll do. We'll have another while. And we'll say if get C is equal to EOF, then what we'll do is we'll say return if the count is equal to 0. Otherwise, we'll compare it not with EOF, but with 1. And then we'll do count minus minus. And then if it's not one of the, and if it's not that, then we'll say otherwise return false. Okay? And so what this program does is it's going to start off with a 0 in the count. Every time it sees a 0, it's going to increment the count. And whenever it sees anything else, it's going to break and go to the next loop. Then into this loop, whenever it gets to an EOF, it's going to compare the count to 0. Whenever it sees a 1, it's going to decrement the count. And if it sees anything else, i.e. if it sees another 0 or some other character, then we're going to return false. So this right here appears to work, because what it does is it would, if we ran it on a string like 0, 0, 0, 0, that's 4, 1, 1, 1, 1, then what's going to happen is we're going to increment 4 times. We're going to go 1, 2, 3, 4. Then we're going to see that 1 and go down to here, and then we'll subtract 1, and then we'll get 3, 2, 1, 0. I guess there's a few. One of the things that we need to do is we need to do ungetC here. And ungetC there is going to put the character back in. Okay. Now, this program right here, we can clearly write down. But is there any difference between the idea of 0 to the n, 1 to the n in this program? And it turns out that there's actually a big difference. And here's the big difference. When we wrote down right here int count, what did we really mean? Well, what we meant was a signed number that took 32 bits. And a signed number that takes 32 bits is a number between negative 2 to the 31 and positive 2 to the 31 minus 1. So that means that if we gave a string that had 2 to the 31 zeros followed by 2 to the 31 ones, then this program would crash. Well, sorry, it's not that it would crash. It's that it would lose track of how many zeros there were, because this count right here would overflow and go back around to the top. Now, we can imagine that rather than using an int, we could use something like an unsigned int. And now we've made it so we have one more bit, that signed bit. So now we can deal with numbers up to 2 to the 32 minus 1. And then maybe we could change it so that rather than using an int, an unsigned int, we could use an unsigned long. And then it would work for numbers up to 2 to the 64. And maybe we could use like a big number library like there are in Java, and you could use the GNU multi-precision number library. It's called or the GNC math. I don't know what it stands for, but it's GMP. It's a way to get big numbers in C. And the thing there is that we could only have as many bits as there is memory on our computer. And our computer will eventually run out of bits, and will eventually stop being able to keep track of what the count is, and will eventually forget. So that means that this program right here is actually only a subset of the possible pieces of 0 to the n, 1 to the n. In other words, this program that we wrote, it's more like a related language that let's call it, what's the right way to write this? Let's call this language equal k. And equal k is the set of strings 0 to the I, 1 to the I, such that I is less than or equal to k. And what I just wrote was I wrote equal 2 to the 31 minus 1. That's the version that uses int. And the version that uses unsigned int would be 2 to the 32 minus 1. And the one that used an unsigned long would be equal 2 to the 64 minus 1. Okay? And the one that used, all the memory on my Mac would be, equal, I don't know how much I have. I have like 16 gigabytes. So it would be like, 2 to the 16 gigabytes. So I don't even know what that is. So a gigabyte is like 1K. So it would be 16 times K times a gigabyte. Actually, I guess those are tens. So it would be never do math in public. So let's see, so 16 would be 4, so it would be 4 plus 10 for the K, plus 10 for the megabyte, plus 10 for the gigabyte, plus 32 because it's bytes. So I guess that's how much memory I have. It doesn't sound right, but I don't know. It doesn't really matter. Okay. So the thing is that even if I dedicated all the memory on my machine, I would still only get a small piece of it. Now, if we wanted, we could write by hand an example of this. So let's write, equal 3. Why do I say 3? Because it's going to be a pain to write. So we would have 1, and if there's a 0, then it would go here. And if there's a 0, it would go there. If there were another 0, it would go here. And if there were another 0, then it would go to this state, which is just going to loop on 0 and 1 because there's too many. Okay? So then, up to here, now there's been 3. So if there's a 1, we'll go there. If there's a 1, we'll go here. If there's a 1, we'll go here. And then that's where we accept. Okay? And this state right here, if we saw 1, 2, 3, 1, 2, 3, what if we saw 1, 2, and we saw another 1, then we would want to go there, because then we would see 1, 2, 1, 2, and if we saw this one, then there would be a 1 down to there, so 1, 1. Okay, so this machine right here is equal 3. It will work for, and of course, if we saw a 0 there, or a 0 there, and then there's a 0 or a 1 there. Okay, so this machine right here, and I guess we also have to say what happens if there's a 1 there. 1. Okay, so this picture right here is the machine for equal 3. Now notice that this machine has a finite number of states, and the number of states has to do with how big that 3 is. Basically, we're going to have 1, 2, 3, 4, 5, 6, plus 2 extra ones. So we're going to have, how can we write this? So equal n is, if we use this structure right here, is going to have 2n plus 2 states. All right? So that means that if we have a certain amount of memory on our machine, then this is going to tell us how big of a DFA we could run, because we know that DFAs take an amount of memory that is the log of the number of their states. All right. So this tells us that my machine has some limit for how big of an instance of this 0 to the n, 1 to the n problem I can run. So let's take that intuition that we've just built for this problem and go back and try to do the proof about the negation of RPP on this. So recall the way that it works. The first thing is that not RPP on this language A, in this case A is equal to 0 to the n, 1 to the n. The first step is it says for all p inside of n. So that means that we are given p and we don't know what it is. It's just some number. It could be 17, could be 1,000, could be 82, we don't know. Okay? Now the next thing is that we're going to have an exists of an s inside of A where the length of s is greater than or equal to p. That means that we need to choose a particular s that has this property. So how could we choose something? Well, because it has to be longer than p, that means that we have to pick a particular thing that we know whose length is going to be greater than p. Now, the easiest way to do this is to come up with a formula for something that we know is in the language that involves p. And so here's a really simple option. We could choose s equal to 0p, 1p. That's definitely in the language. We know it's in the language because it has an equal number of zeros and ones, and we know that its length is at least greater than p because we know that its length is 2p. All right, great. Next, there's a for all x, y, z inside of sigma star, such that s is equal to x, y, z, and the length of x, y is less than p, and the length of y is greater than 0. Okay? Now, we don't get to choose those. They're given to us. So that means that we've been given some strings x, y, and z. And we don't know what they are. Our enemy, the person who's trying to thwart our attempt to do this proof, they've come up with them. So what's the right way to think about this? So what we want to do, whenever we have some situation like this, where we have some large number of possibilities, we want to break down what the options are. So we know that our string was 0p, 1p. And it's been divided up into 3 pieces, x, y, and z. Okay. So what we need to do is we need to imagine that there's some boundary between the zeros and the ones. So we know that x, y, and z has some number of zeros and ones. But here's something interesting. Is it possible for z to have any zeros in it? It turns out that it's not possible because we know that the length of xy is less than p. And so since we know that there are exactly p zeros, that means that all of those zeros has to be consumed, you might say, by, that if z had any zeros in it, then that means that x and y would be, what I just said about zeros, we really want to think about ones. Okay, is it possible for x to have any ones in it? It is not possible for x to have any ones in it, because if it did, then that means its length would be all the zeros plus at least 1p. So that means that we know that x has to be equal to some number of zeros. We'll call it 0 to the a. Now, what about y? Can y have any zeros in it? Any ones in it? No, it cannot. Because if y had a single 1 in it, then that means that x and y together would have all p zeros plus at least one 1, and that means its length would be greater than p. So that means that y has to be some other number of zeros, which we'll write as 0b. Then z, of course, has the remaining zeros and then all of the 1s. Okay, so we know that these rules determine that. So we now know, let's write this as like a system of equations. We know that a plus b plus c equals p, and we know that a plus b is less than p, and we know that b is greater than 0. Because we know that the length of y is greater than 0, and we know that the length of x and y together is less than p. All right, now what's the next step? The next step is that we need to show that there exists an I inside of n where x, y, I, z is not inside of a. That's what our job is. Well, what is x, y, I, z? Well, x, y, I, z is equal to 0 to the a, 0 to the b to the I, 0 to the c, 1 to the p. And when is that inside of a? That is inside of a if and only if a plus bi plus c equals p. Okay, well, we can subtract a plus b plus c from both sides, and so we can subtract that. So we'll get a minus a is 0, c minus c is 0, p minus p is 0, and then we will get bi minus b is equal to 0. So we'll get b minus 1i is equal to 0. Did I do that right? No, sorry. We have bi minus b is equal to 0. Okay, well, we can factor out that b, so we'll get bi minus 1 is equal to 0. Now, we'd like to divide by b, and we can divide by b because we know that b is greater than 0, so now we have I minus 1 equals 0, which means that I equals 1. So that means that this property is true only when I equals 1. Therefore, since our job is to choose an I where it's not true, let's just choose I equals 0. And in that case, we know that the string that would pop out would be 0a, 0c, 1p. And we know that that is not inside of a because we know that a plus b plus c is equal to p, and b is greater than 0, so therefore a plus c cannot possibly be equal to p. Thus we've shown that the language 0 to the n, 1 to the n, which is definitely a subset of the possible strings, does not have the regular pumping property, and therefore is not a regular language. This is actually a really crazy idea. The reason that this idea is so crazy is because something that we never really alluded to we never really spent too much time talking about in the past, is that all is all possible computations. Okay? And we just showed that something inside of 0 to the n, 1 to the n is in all, but not in reg. Okay, but why do we care about reg? Well, it turns out that reg is all DFAs. And guess what? DFAs are all physical computers. Let me put that another way. All physical computers are modeled by DFAs. Whatever you're watching this on, it is really a giant state machine. So Inside, there are registers, there's the memory, there's whatever's going on with all the flags and stuff like that. And it's a little automaton. And you can kind of think of it as like the characters that are being read in are not characters 0, 1, etc. Instead, the characters being read in are like the opcodes of the assembly of the language, of whatever the architecture is. And those assembly instructions, they come in, and what they do is they modify the state of the machine, and they update it to the next state. And that's really what your computer is doing. Your computer is really just a giant DFA going through all of these different interactions. Now it's of course connected in like a network of other ones, and you can kind of think of those as being like different input signals. So I'm not saying that we perfectly know what's going to happen with all computers, because we don't know what input string they're going to get, but we do know that their state is finite in this way. And in fact, any physical computer that could ever exist would be finitely large too, because we know that there's only a finite amount of the universe that we could touch. I'm not a physicist, but my understanding is that we don't have any way to access infinite sources of information. So basically what this means is that we've just shown that this language, 0 to the n, 1 to the n, is something that we can never solve. That whole thing that we talked about before, the equal k, where we have some piece of it, we can solve any subset of that problem, but we can't solve the entire thing, meaning that we can't write a program that will work no matter how big of an input it's given. And so this basically tells us that there is something just like fundamentally limited about the kinds of computations that our real physical computers can do. We can define computations like 0 to the n, 1 to the n, but we can't actually run them. And it turns out that once we know that 0 to the n, 1 to the n is not regular, we can actually derive an infinite number of other things that are not regular. So for example, we know that 0 to the n, 1 to the n is not regular. Suppose that B were some other language that was regular. Then it would be the case that 0 to the n, 1 to the n, circ B, would also not be regular. I think there's only one circumstance, except when B is equal, B not equal to the empty set, because then it would be empty. Okay. And since we know that there are an infinite number of regular languages, we now know that there are an infinite number of non-regular languages. At this point, we've now gotten to the place where we can where we've now gotten to the point where I can reveal the structure of the rest of the class. The whole point of the rest of the class will be to take the space between all and reg and divide it up into more divisions. We started by saying we've got all and we've got fin, and what I just did is we just showed that there's this spot reg that's in between them. Okay? For the rest of the class, what we're going to do is we're going to divide this space up even more. We're going to divide it first into a category called the context-free languages, CFL. Then we're going to divide it into what are called the decidable languages. Then we're going to divide it again into the recognizable languages. And these three categories are going to be new kinds of machines, new kinds of computations, new theories, and ultimately we're going to show that even the widest one of these is also not all, and that there's going to be something that is inside of all that's not inside of sigma 1. Something that's inside of sigma 1 that's not inside of sigma 0. Something that's inside of sigma 0 that's not inside of CFL. Something that's inside of CFL that's not inside of reg. And what this does is it gives us a hierarchy of different kinds of computations and different kinds of computers. The regular ones are essentially ones that we can actually run in the real world. The CFLs are ones that are, what's a good way to describe this? They're like easy to run with a limited amount of memory or something like that. The citable ones, they're ones that when you run, you know you're going to get an answer back. They kind of are like programs that don't have errors in them. Sigma 1 are programs that you can write down, but they might have errors and they might have infinite loops. And then there's going to be more computations that we can't even write down programs for. If you write down a program, you have no way of knowing if it's possibly right. And ultimately, this class is about a big, giant, pessimistic thing, which is that computers can't do everything. And here, the notion of computer is actually much broader than just saying like hunks of metal can't do anything. Because I think that most people would agree with the idea that, like, I don't know, computers can't fall in love or something like that. You know what I mean? But when we think about problems, like computational problems, mathematical equations that we are interested in, computers cannot do all of those. And it's not only that computers can't do them, but in fact, even humans can't do them either. And the reason why humans can't do them is because algorithms can't do them. And algorithms can't do them as well as programs can't do them. All of these things are all wrapped up in one idea, because when we defined the idea of a computation, we didn't, we didn't say anything about it related to like physical hardware or bits or anything like that. We had this more general idea about what it is, about what a computation is. Now, I just want to say one more thing about this. This 0 to the n, 1 to the n language, it's not the only thing that we could do a proof about the negation of the pumping property on. There are lots of things we could prove are like this. So some classic things that people like talking about is the set W, where W has an equal number of 0 and 1. Here it's not that they are it's not that they are all in order, it's that there's an equal number of them. Another example would be WW, where W is inside of sigma star. So this one is a string followed by the exact same string. Another one would be WWR, where W is inside of sigma. This is where we have a string and then that same string reversed. Another one would be something like 1 to the n squared, where n is a natural number. Here we're showing that we can't count the number of ones. Another thing that we can't do is we can't do something like 0 to the I, 1 to the j, where I is greater than j. This one shows that we can't compare things. There's one last that I would like to point out that I think is interesting. So let's imagine a way to recognize correct addition equations. Because remember, way back at the very beginning, one of the things that we said that the people who came up with this field wanted to do is they wanted to come up with a way of looking at a math equation and saying whether or not it was correct. So let's think about a way to encode equations like 1 plus 1 equals 2, or 2 plus 3 equals 5. These are true equations and we'd like to accept them, but if we had an equation like 2 plus 2 equals 1, then we'd like to reject that equation. So here's a really simple way to encode these as binary problems. This first one we would write as 0, 1, 0, 1, 0, 0. This next one we would write as 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0. This one we'd write as 0, 0, 1, 0, 0, 1, 0. Do you see what the pattern is? The pattern is that we have x zeros followed by a 1, then y zeros followed by a 1, and then we have x plus y zeros. Okay, so this language is not in reg. And here's a little proof of that. So first we have the for all p. So we don't get to choose what p is. Then we're going to choose an example s. So let's choose the example s, 0p, 1, 0p, 1, 0, 2p. Now we have a for all x, y, z. So like before, we know that x and y can only contain zeros. So we know that x is some number of zeros, y is some number of zeros, and then z is some number of zeros followed by 1, 0p, 0, 2p. Now we know that the only thing that can change is the number of zeros here. But the only way to make it so that this equation is right is that if we change them on both sides. You can kind of think of it as what the what the regular pumping property does is it allows us to add zeros here or remove them, but it can't change anything there. So in other words, it allows us to write something. If we take the equation like 2 plus 2 equals 4, we can take this and change it to something like 8. But it will still say 8 plus 2 equals 4. We won't be allowed to change that 4 into a 10 because we can only change this y component. So this shows us that it's not possible to do that. And we can basically show that any I that's not 0 will fail. Sorry, that's not 1 will fail. Okay. So what this shows us is that our computers cannot even identify correct addition problems. And that is very depressing, because it would certainly be nice if our computers could do arbitrary addition. They, of course, can do addition on any fixed amount of bits. Right? We can make a variation. So let's call this the add problem. And we could make a variant of the add problem that was the add k problem, where it was 0x1, 0y, 0x plus y, where x and y were less than k. And so a problem like that we could do. And that's kind of the way that all computers actually work. There's some amount of math that they can do based on how much memory they have. This is a good time to stop. What we'll do next time is we'll begin our quest to divide up this region between all and reg, and we'll start with the category known as the context-free languages.